Hello, my name is Valeev Dmitry. I am a senior researcher from Vernadsky Institute of Geochemistry and Analytical Chemistry, and today I want to tell you about a new method that I developed in Russian Academy of Science. This method was about new technology to production alumina from alumina-containing wastes. I'm happy to welcome young scientists that take part on the Lomonosov conference. My name is Valeev Dmitry. I am a senior researcher from Vernadsky University of Analytical and Geochemistry of Russian Academy of Science. And today I want to tell you about new method in non-ferrous metallurgy. I want to start my lecture from a quote by Mikhail Lomonosov. Let's say very interesting quote in his report on the Russian Academy of Science in Russian Empire in 18th century. He said that between different parts of science, types of science, the metallurgy is on the first place because scientists on metallurgy need to find and purify the metals and other minerals, and this have the big application in the human's life. So my presentation is about new method to produce alumina from coal fly ash. Coal fly ash is waste from coal power plant, and I want to answer these five questions. What is alumina? What is the coal fly ash? What's the history of alumina production? Why today use alkali in alumina industry? And why you need to use acid to leaching aluminium from aluminum-containing materials? And I think that it's very interesting to young scientists understand that metallurgy consists from four big groups. The first is enrichment processes that mainly used in gold metallurgy. The enrichment processes use gravitative methods to separate different type of minerals, and you can see on the slide the equipment of the enrichment processes. The next group is the hydrometallurgy. And we use hydrometallurgy to extract non-ferrous metals using a different solution and liquor. And if we use these reactors, the temperature of the processes are not more 300 degrees. Pyrometallurgy is the third group. We use these methods when the temperature was higher than 700 degrees. And we use different furnaces to smelt the ore or different raw materials and produce two types of materials. It's the slag and it's the metal. And we can separate metal and the slag is the waste. And the last groups is the electrometallurgy. It's very interesting methods because we can use it in solutions and in the furnace. If we use it in solutions, we can produce purified copper in copper metallurgy. And if we use the furnace and electrolysis in the furnace, we can produce metallic aluminium. So the first question is, what is alumina? Alumina is a white powder that need to produce metallic aluminium by electrolysis process. Aluminium produced using bauxite ore, and bauxite has the red color because in his chemical composition have big part of the iron oxides. And if we need to treatment bauxite, we use Bayer process. But the first I need to say some words about aluminum production. From the last 20 years, the aluminum production have increased for 3 times, from 25 million tons to 65 million tons. And the most biggest production in China. And in this slide you can see the largest companies that produce metallic aluminum, and the Russian company that called Rusal on the third place with 3.8 million tons of metallic aluminum. The Bayer process is the main process to produce alumina from bauxite. Karl Bayer is an Austrian scientist that worked in Russian Empire in the end of the 19th century, and he worked in alumina refineries and developed and intensified different metallurgical processes. And the first method is that he found is the precipitation method. He found that if we add small particles of aluminum hydroxide into aluminate solution and increase temperature to 60 degrees, at the same time we can see that all aluminum in the liquor can precipitate in aluminum hydroxide form, and alkali we can reuse in the leaching process. And this aluminum hydroxide is very purified, and using calcination of this powder we can produce aluminum powder. So in the next 3 years he intensified the leaching process. If we use a simple reactor and using leaching with atmospheric pressure, the aluminum extraction degree are not more 50%. But if we use the special reactors that called autoclave or we can extremely increase the aluminum extraction degree from 50% to 95%. And these two methods today used on the all alumina refineries in the whole world. And in this slide you can see the principal flow chart of Bayer process, and I tell you about the main stages. The first, when we need to crush bauxite, and we use special rotary mill. After crushing and classification, we need to leaching bauxite in alkali, and for this method we used high pressure reactors. After leaching process, we need to separate solid residue from the liquor, and solid residue called red mud, and is a very hazardous materials, and if we produce 1 ton of alumina, we can generate about 1.5 or 2 tons of red mud. This red mud goes to special landfills and have a big impact for the environmental. Liquor after filtration goes to precipitation processes, where we add 25% of seed aluminum hydroxide, and after precipitation, aluminum hydroxide goes to calcination process at 1200 degrees temperature. And for this process, using the largest furnace in the metallurgy, it's called the rotary tubular furnace. And we can produce alumina from bauxite. It's a very simple process, but if we use this process, we need to use special type of bauxite. How we can understand what type of bauxite we used? We find the interesting criteria. It's called silicon model. Silicon model is the he shows how much alumina and silica in bauxite, and if this distribution more than 7, we can use simple Bayer process. And if this factor about from 3 to 7, we need to use modified Bayer process with sintering method. And only in one aluminum refinery that located in Russia, in Achinsk, then use Keoxaltar-Nephelin. We use a sintering process to treatment the ore that have silicon model lower than 1. But in Russia we have many types of different materials that can also be used as raw materials to aluminum production. And some of them named ash, and they have the similar chemical composition as in Keoxaltar-Nephelin. But we cannot use sintering processes. Why? We have 4 big problems in the sintering processes. The first of them is in this type of ore we have very big content of silica, and we need to modify this phase from silica to calcium silicate. And for this we use special method that called primary roasting method. And for this process we use special equipment. It's the tubular rotary cleans. It's the largest furnace in the metallurgy. So by the leaching process we can lose some of alkali that dissolve silica. And all these factors provide that alumina cost is very high. So this method we cannot use to produce alumina from ash, but we can use another method, and one of them is the acid method. I developed the hydrochloric acid method. It have some advantages compared to other acid. It's more efficient process if we need to extract maximum of aluminium from ore to the liquor. If we use the hydrochloric acid, we can reuse this acid to the leaching process, and we can use the aluminum salt, aluminum chloride liquor as a coagulant to water purification. And in this liquor have a high content of the rare earth elements like scandium, and we also can extract it by solvent extraction or sorption by resin. And in this slide you can see the simple flow chart to understand this process. When we use the raw materials, after we leaching it in acid, after filtration we produced a liquor, and we crystallizate aluminum salt from this liquor, and after calcination we produced alumina. And the main advantage of this process is silica are not have reaction with hydrochloric acid, but iron oxide are also dissolved like aluminum oxide. So we need to understand how ash was generated on the power plant. When we use coal to produce electricity and heat, after combustion process we have waste. If these particles are heavy, this named bottom ash. If these particles are fine, they called fly ash. And if we combustion 1 ton of coal, we can produce from 100 to 500 kilograms of waste, and 90% of this ash was fly ash, and only 10% of this ash was bottom ash. And my research is about fly ash utilization. And we need to understand the world experience in utilization processes. The developed country use ash in construction industry and in road construction industry. And you can see that utilization rate in this country are very high. So only in China using ash as a raw materials for metal extraction. What about Russia? In Russia in 2019 produced about 20 million ton of ash, and only 8% of this amount was utilized in construction materials. It's a very small amount, and we need to increase it to 50% for the next 5 years. This map demonstrates the geographical distribution of the coal power plant that located in Russian Federation. And you can see that the most amount of coal power plant located in the Siberia and Urals. And the blue color, we can see the name of alumina refineries that located close to this power plant, and it is we can use this ash from this power plant and go and use it in these alumina refineries as raw materials. On this map, you can see the total amount of ash was accumulated in landfills of these coal landfills. So in my research, I used two types of ash, the Omsk ash and the Raftinskaya grass ash. This power plant used Ekibastuz coal from Kazakhstan Republic, and they have the very similar chemical composition. This both power plant produced about 5 million tons of ash per year, and the total accumulated about 200 million tons of ash. And the main components of this ash is silica, is about 60%, and aluminum oxide is about 25%. The main mineral phase is magnetite, quartz, and mullite. And in this slide, you can see that flow chart that I developed. They have the 4 big stages, and I tell you about each of these stages. From this gray ash, we can produce 3 main products. The first is alumina, is a white powder. The second was metallic iron powder. And the third is a coagulant polyaluminium chloride that can be used as a reagent in water distribution system. And in this slide, you can see the mass balance of our flow chart. That if you used 100 kilograms of ash, you can produce 25 kilograms of alumina. The first stage is very simple. It's the magnetic separation. We have magnetite in this ash, so we can separate it from the non-magnetic fraction of the ash. And we use different equipment to these processes, and you can see it on this slide. Magnetite located on the surface of the alumina silicate spheres, and it have different shapes. You can see it in these same images. It may be separate pyramid forms or dendritic forms, or another interesting forms. In the left of this slide, you can see it. So we can see that we cannot fully separate the iron from the surface of this spherical particles from aluminum silicate. And the maximum content of iron in the magnetic fraction not higher 50% of iron oxides. And when we analyze this ash by mass-Bauer spectra, we can understand that in the raw ash we have iron in magnetite form and in separate ion that located in the aluminum silicate spheres. But after magnetic separation, in magnetite fraction, iron only in magnetite. But in non-magnetic fraction, we have very high content of iron, is about 2% to 8%, and it's on this individual ions of iron that located in the aluminum silicate spheres. So the second process is the frost flotation. We use it to separate unburned carbon from the non-magnetic fraction. The carbon is hydrophobic particles, and non-magnetic fraction is the hydrophilic particles. We used a special collector, is a diesel fuel, and a special former agent to produce big part of oxygen bubble in this liquor. And we can separate unburned carbon to the individual fraction with the carbon content about 25 or 30% of carbon. So the third stage of my research is about interesting process to separate iron from the surface of the ash to individual particles that can be simple separate by magnetic separation. We use special processes that called carbothermic reduction roasting, when we can smelt these particles and these small particles coagulate into separate one big iron particle. In this slide you can see how we realize these experiments. On the left of this video we started the experiments, and of the second you can see how we cool down our samples. We need to prevent our iron particles to oxidation process, so we cool down in liquid nitrogen, how you can see in this video. So we use different flux to intensify this process. If we use only carbon fraction is a reduction reagent, we can increase these iron samples and separate it. You can see it in the optical image on the right, in the upper on the slide. But if we use special addition like sodium carbonate or sodium sulfate, we can radically increase the particle size of iron metallic sample. And you can see it in the bottom of this slide. The particle size was about 100 micrometers, and we can fully separate it from non-magnetic spheres. In the magnetic fraction, the iron content was about 30%, and after our reduction roasting, we can produce iron powder with iron content about 95%. It's a very good results. After reduction roasting process, we produced non-magnetic fraction, and we need to extract aluminium from this fraction to solution. If we use hydrochloric acid in atmospheric pressure, the aluminum extraction degree are not more than 5%. And we change the temperature of the process and the hydrochloric acid concentration, but it's no matter, and alumina extraction efficiency are not more 5%. And we need to intensificate this process. We use a special reactor, high pressure reactor, and if we use temperature from 119 to 210 degrees, we can radically increase the extraction of alumina to 90%. We also change the concentration of hydrochloric and found that if we use 30% hydrochloric concentration is the best for our process, and we can extract more than 90% of aluminum to the liquor. And some words about the mechanism of the leaching process. This aluminosilicate particle consists from two oxides, aluminum oxide and silicon oxide. And raw ash have 50% of silica oxide and 50% of aluminum oxide. And after leaching, we can see that some of main part of aluminum are dissolved, and you can see it in the bottom of this ash in the right. But we have unreacted core in these particles, and aluminum in this core are not reacted with hydrochloric acid. And if we saw this table, we can see that not all aluminum we can dissolve, because some of aluminum are not dissolved and located in this unreacted core. We analyze the physical properties of these particles before and after leaching process. The average particle size distribution are not have the big difference, but the big difference was in a specific surface area of these particles. The raw ash have about 8 square meters per gram, and after leaching process we have about 14 square meter per grams. And we have the interesting idea. So if we increase this specific surface area of raw ash, we can increase the aluminum extraction degree in the leaching process. And with my colleagues from Ural Federal University, we realized interesting method to preliminary alkali leaching of ash. We can leach only the surface of these particles and destroy this silica from the surface, and we can extremely increase the specific surface area from 1 square meters per gram to 15 square meters per gram, and it's a very big volume. So if we use these particles with a high specific surface area, the reaction with hydrochloric acid was fully, and we can decrease the temperature, the hydrochloric acid concentration. And we produce these experiments. You can see it in this slide. We can extract more than 19% of aluminum if we used 119 degrees temperature and 20% of hydrochloric acid concentration. And our ash particles after leaching process have the very high specific surface area volume, is about 15 square meters per gram. it's a very high volume. The next stage after leaching and filtration, in our liquor we have high content of rare earth elements. The most interesting of them is the scandium, and its content is about 2 milligrams per liter. It's a high content, and we can extract it using sorption methods. In my research, I use the industrial type of resin, the Fluoride type. You can see this shape of this resin is the spherical particles, the big spherical particles. And in our experiments, we change the ratio of these resins to liquor, and we change the temperature of the liquor. So we found that main impurities is aluminium, iron, titanium, alkali, potassium, and others are not extracted to the resin, but only titanium extracted to the resin, like scandium. And if we increase the temperature from 25 degrees to 55 degrees, we can decrease the duration of the process from 1 day to 6 hours. We can extract about 90% of scandium from liquor to the resin. And our future research is about how to separate the scandium from titanium in this resin. The next application of this liquor is about using this liquor as a coagulant. Coagulant needs to purify water in water distribution system. And the mechanism of this process you can see on this figure. If in the water we have different impurities, it can be organic or non-organic impurities, and all of them are in colloidal form. And we need to separate it from the water. If we add a small amount of this coagulant, we can coagulate it in big particles, and they goes to the bottom of the reactor, and we can separate it from the purified water. And we use our experiments for the Moskva River water. You can see its characteristics in this table, and we need to decrease the turbidity, chromaticity, and the permanganate index of this water, and we using the Russian drinking standards, that's the same as World Health Organization standards. So we can use this coagulant not only in Russia and in other countries too. When we produce our experiments, we compare our reagent with the industrial reagent. It's a coagulant from Aqua Aurat 18th. It's a very famous type of coagulant. And we found that if we use 4.5 dosage of 4.5 milligram per liter dosage of coagulant, we can fully decrease these parameters, and the iron and aluminium content in the purified water was very low. And we can use it to produce drinking water in the real processes in the water distribution system. So the next stage, it's the last two stage is about alumina production from aluminum chloride solution. We need to precipitate the aluminum salts from aluminum chloride solution, and for this process we used a special method that's called salting out method. When we used hydrochloric gas and bubbled it through the liquor, we can decrease the solubility of aluminum chloride in solution, and when the hydrochloric acid concentration in this liquor is about 36%, the aluminum salt was precipitated on the bottom of the reactor, and you can see it in this figure on the left of the side. We found that temperature of the liquor have a great impact for the yield of the aluminum salts. If we decrease the temperature from 95 to 0 degrees, we can increase the yield of aluminum salts to 99%. And the shape of the crystals you can see of the electronic images on the right hand side. When we produce these aluminum salts, we need to delete the chlorine ion, and the water content. So we need to use the special process, the calcination process, and we need to increase the temperature in the furnace from room temperature to 900 degrees temperature. And this calcination process have two stages. The first stage in 200 degrees, when the big part of chlorine ion and water was deleted from these aluminum salts in the gas, and we can produce special type of powder, the amorphous alumina. You can see it in the inner of the side, upper of the side. These particles have pores on the surface, but these pores are small and not on all the surface. And if we increase the temperature of calcination to 900 degrees, we can increase the pores amount on the surface of these particles, and you can see it in the bottom of this ash. So these alumina powders have the same shape of the aluminum salts. That's the big hexagonal particles, and we can see that the average particle size distribution of this powder are very high, and the most important criteria of this powder is the chlorine ion content in this alumina during calcination process. In the amorphous alumina, we have about 5% of chlorine ion, and in the centigrade alumina, we have about 0.15% of chlorine ion. And it's a very big volume of chlorine, and in the further electrolysis process, we cannot use this alumina and cannot produce metallic aluminum from this alumina. So we need to modify this process, and we use the special recrystallization by alkali. In the left, we can see that aluminum salts is a big hexagonal crystals, and when we produced amorphous alumina, when we calcination these salts in furnace at 400 degrees temperature, we produce amorphous alumina, and the shape are the same. It's a big hexagonal shapes. But we need to produce spherical alumina, like in this photo on the bottom of the slide. So we use the special recrystallization process. You can see the flow chart on the center of the slide. We have the interesting idea. If we use this amorphous alumina with high chlorine ion content, we can dissolve it in alkali and produce from this aluminate liquor the aluminum hydroxide, and further we can calcination this aluminum hydroxide and produce alumina. And we used the special reagents. The first is the aluminate liquor. We use the real aluminate liquor from Bayer process, from the real Bayer process after precipitation stage. We use this liquor from the Urals alumina refinery, and the next reagents was the aluminum hydroxide, the coarse aluminum hydroxide. It's a product that can obtained in this Urals aluminum refinery. And when we mixed our amorphous alumina with a high specific surface area and this coarse aluminum hydroxide, we can dissolve it in alkali liquor. And aluminum hydroxide are not dissolving in alkali because they have very small specific surface area. But our amorphous alumina have high specific surface area, and it was rapidly dissolved in this liquor. And after dissolving, the aluminum ions in the liquor can be precipitated on the surface of this aluminum hydroxide. And this process can be simple called the recrystallization process. And you can see that the coarse aluminum hydroxide have the small average particle size distribution. And after our process, we can increase this amount from about 18 micrometers to about 100 micrometers. And when we produce this aluminum hydroxide, we can use it in a rotary tubular furnace and in calcination process, and at 1200 degrees of temperature we can produce alumina which have the shape, the spherical shape, and this shape can be used for the further electrolysis process and aluminum metallic production. And the most interesting is the chlorine ion content in this powder. You can see that this very low content of chlorine ion, and we can use this alumina as raw materials for aluminum production in the electrolysis processes. So that's all my results in my research, and I need to say thank you for your attention. And if you are still awake, I will glad to answer your questions. And I have the first questions. Is it theoretically possible to reach 200 iron content in the iron powder? It's very interesting questions. No, we haven't produced powder with this high content of iron, because we also have different impurities. But we can produce iron powder with 99% of metallic iron in this powder. I think we can produce it. And the second, what I need to say, it's about yield of iron powder from the carbothermic reduction processes, because our experiments show that yield was very small, and we have the big losses of iron in the slag, and we need to increase the yield of the iron powder, not increase the iron content. We need to increase the iron yield of the iron powder. That's all. Okay, that's all the last questions. And I need to say thank you for all young scientists, and see you later.